Hey, Laurie. Hi, Scott.
Hello. And a bunch of the students are here too.
Good. And Pete, is Pete here yet?
I am. I just joined. Hi, Ed. How are you doing?
Oh, Pete, how are you? What a pity to not be able to meet in person and enjoy a beer and a meal together.
I know. I'm very sad that hasn't happened as well. But anyway, maybe some later time we'll be able to manage it.
I hope so. And I hope sooner rather than later.
Right, for sure. Do you get, let's see, you don't have my video feed, do you? So I'm trying to work out, here we go, start video.
In fact, I found a rather cool thing. There.
Great. Is that a Zoom background that you can switch in on and off?
Oh no, I happen to be up in my spaceship at the moment, so it's just if you go to the bottom where it says the audio, the video on and off, there's a little triangle, and if you click on that, it says something about backgrounds, and then they have a whole bunch of pre-defined backgrounds.
Oh, that's
so
cool.
Pick one and download it, and then there you have it, and you can switch it on and off.
That's really funny.
The students are quite creative with it. Maybe we could ask one of them to demonstrate.
Oh, really?
Oh, yes. They've been in all kinds of places in their backgrounds.
Oh my.
So, hi, Peter. Alan here. I have a dull, boring background, but I heard that an unspecified computer science professor had made a video as a background of him just sitting there going, yeah, okay.
Oh, I like that.
And I have no idea who it is, and it now worries.
That's great. I love it.
Yeah.
It's good to see you, Alan. It's been a while.
It's been a while, Peter. Nice to see you.
You might not know, Alan and I were in Edinburgh together in rather too many years ago.
Yeah.
So
in some previous millennium.
Yeah.
You were roommates or graduate students?
We were. Alan was doing his PhD at the same time as I was doing my masters, so we used to hang out together quite a bit.
Yeah.
Oh.
A long time ago, but yes, he's done well for himself, actually.
As have you.
These youngsters, Alan. Yeah.
Yes.
Right. Yes.
So no student chooses to demonstrate an interesting customized background? Any volunteers?
I like Scott's. I like Scott's background, actually.
Yeah, it looks like I'm in my study at home, doesn't it?
Yes.
That's scholarly.
It's small enough you can't read the titles on the books.
Which is the important point.
Right.
Because they repeat, don't they? Yeah.
Well, maybe they're just virtual books. It's another selected background.
It's possible. The dinosaurs show up later in the background, but for now it's just books.
There we go. We have somebody else showing a background? No, no background.
No, they don't want to give away their secrets to the
There's one. There's one. There's one.
Oh wait, who is it?
Oh, yeah, it's even better. It's even better.
Cool. How do you do this? You wear a green shirt?
I'm not seeing who it is.
So, because you've got a cool font as well, it's Brendan.
Oh, Brendan. Okay.
So, Brendan, what do you do? You wear
you could probably see my picture.
You have a green. You have something green or something, and then that's
it's just
like in the movies.
You can also just select the color. So if you're wearing like a brightly colored shirt, you can also just use that.
Oh, and then you can have the background also display, so it looks like you're invisible except for your head or something.
Yeah, if I took a picture of the background, then I could make it look like an invisibility cloak.
Excellent.
Fantastic.
Very cool. As I see my audio is coming through, okay?
Yeah.
Good.
Yep.
Good.
So, Pete, usually the talk is about an hour-ish, plus or minus, and then usually there's questions in the middle or at the end. And at some point people go off and have cookies, which is now no longer possible. So we'll have to see about the cookies there.
All right, you can send them in the mail.
So, Ed, I'm not sure if you are aware of the change in schedule. Usually the speaker meets with students in the morning, but because we didn't want to make Peter meet with students at 6:30 in the morning, they'll be meeting with them after the colloquium. So starting at 4 o'clock, he has a few individual meetings with students.
Oh, that's great. Okay.
Yeah.
So Laurie, how do you usually do the questions? People just pipe up, or is there somebody who points, when people point up their hand, put up their hand and somebody selects them? Or Pete, you do that, right?
Yeah, so people can either just unmute themselves to ask questions, and also if they would rather raise their hand, then Divyansh and I will keep monitoring the participant list to see if hands are up.
Yeah, I think you should do it that way, or it's too hard to cut in by audio.
Yeah. Okay, this is Bob, right?
Yes, hi.
Oh, that's Luke Skywalker.
Yeah, looks a little like me.
Okay, so we will monitor when people's hands go up in the participants list. Do they come to the top of the list?
Yeah.
Oh, I see. Somebody's hand is up now.
So
Thank you, Salvador.
So I can unmute that person. Okay. Okay.
And I'll stop every few minutes to ask if there's any questions as well, so people get a chance.
Okay. Actually, these Zoom meetings is much less painful than I expected them to be. So it may be the case that from now on, we do a lot more of this meeting this way in the future.
Yeah, I wish I had bought Zoom stock last month.
One of my students did.
Oh, good for them.
We went from $100 to $160 in like 2 weeks.
I bet.
Mm-hmm.
I'll try sharing my screen as well, just to put the slides up.
Yeah, and Ed, whenever you're ready, you can start introducing.
All
Oh,
right.
and I'm going to applaud for the speaker with the sound effect.
Oh, okay. Okay, so Ed will do the introduction and Bob will play the applause sound effect.
Yes.
Okay, so Ed, whenever you're ready.
So it is my great pleasure to introduce an old friend, not as old as Alan Black's friend, but still an old friend, Pete Clark, who's now Senior Research Manager at AI2 in Seattle. On project, he's leading the project Aristo that we're going to hear about today. And he's been doing work in sort of computational semantics around NLP and AI for as long as ever since graduate school. And as you know, semantics is difficult because it's not text on both ends of your transformation. On one end is you've got to make up your representation and there's no correct answer and stuff. So it's slow going, and people who have a lot of patience and are very careful in their research, like Pete, work and slowly uncover all the things that one has to pay attention to in order to get semantics and not just a mess. So his work has been, he's got 3 best paper awards. He's got a large number of papers, over 120 publications in some of the best conferences ever. Before he was at Boeing and Texas, Austin and Ottawa and the Turing Institute and in Vulcan. So he's gone around many places and picked up experiences. And I think you'll hear some very interesting thoughts and thought-provoking thoughts about how you can go deeper in surface-based transformations, which is all the fancy stuff now. But you have to, at some point, go deeper than BERT, and I look forward to hearing what Pete says. So Pete, welcome to us. Thank you for coming to talk to us. We look forward to your talk.
Ed, thank you very much. First and foremost, let me just say I hope everybody is safe and well in this crazy times. It takes a little bit of getting used to. And as I mentioned to Ed earlier, I'm very sad that I can't be with you guys in person, but hopefully in the near future we'll be able to meet up. I'm assuming that you can see my slides, and I've just noticed I've got the wrong date here from an old cover page. I'm going to talk to you about the Aristo project, which I think a lot of you know about, that we've been working on for several years. We had some exciting success last year, so I want to dig into that a little bit. First, let me just mention about the Allen Institute. So we're in Seattle. This building here with the arrow is the AI2 Institute and so on. A good day when the weather's good, we get a nice view across the lake. We see the downtown area. Of course, with the changed working from home arrangements, we've dispersed a bit. So the new branch of AI2, from my point of view, looks like this. So this is my new working environment, and you'll see my one of our dogs, Dobby, who's sitting on my chair here. So she's delighted about having 8 hours of continuous attention every day as I'm working away. So she's my kind of pair programming companion. It's hard to get used to working remotely. The one good thing about it is I have a much shorter commute to work. So this is my new commute. All of 32 seconds to get to work saves me a lot of time compared with the normal trek to downtown. So Project Aristo. So the Aristo project arose out of Paul Allen's grand vision of building intelligent systems. He was a visionary for AI and was always pushing to try to build machines that had deep understanding of the world, who could answer questions. In his book, The Idea Man, he writes, over the last decade, I began to think about a digital Aristotle, an easy to use, all encompassing knowledge storehouse to advance the field of AI. And so the Aristo project came out of that vision. So Aristo is meant to connote Aristotle as a boy, and to try to operationalize this grand vision and reduce it to something manageable, we decided to initially start looking at science and in particular elementary and high school science. And we also chose to measure our progress on how well we were doing about scientific reasoning and question answering using standardized tests, giving the questions exactly as written to the machine. And if you look at some of the science questions in the exams, it doesn't take long to realize these questions are really hard. So here's one example question, which is quite difficult. How are the particles in a block of iron affected when the block is melted? And the correct answer is the particles move more rapidly. And this requires both science knowledge, that high temperatures cause particles to move quickly, and also common sense knowledge, namely, if something is melted, its temperature is increased. So we see these kind of challenging problems all the time looking through the science exams. And I should add, our goal is not to build a test-taking machine. We're not trying to put fourth graders out of work. This is just a means of evaluating progress. And just briefly on science exams as a grand challenge, it's quite difficult in AI to find good grand challenges for the field. We want tests that will measure whether machines can answer a wide variety of questions, answer complex questions, can handle common sense and world knowledge and so on. And so science exams are one great test which involves all these capabilities. And also just from a practical point of view, if you want to have a successful challenge, it needs to be a task that's clearly measurable, it's graded, so different levels of performance. It shouldn't be gameable where you can solve it with cheap tricks. It needs to be ambitious and motivating. And if you go through and look at science exams, they very unusually meet all these criteria. So I think this is a very good challenge to work on. It's certainly not a sole test of machine intelligence. It's just one indicator of progress, but nevertheless, it's rather unique in its characteristics like this. When we started on Aristo back in 2014, we scored about 36% on the non-diagram multiple choice questions. So we've worked on diagrams, direct answer questions, but the multiple choice questions without diagrams are the ones we've focused on in particular, because these are the most prevalent in the exams, and also dealing with diagrams raises a whole slew of other really complicated problems. And these are typically four-way multiple choice questions. So random guessing is about 25%. And these, of course, are measured on a hidden test set of questions which were kept from the researchers. Over the first couple of years, we added in some simple methods using information retrieval and statistical methods, added in a rule-based reasoner, and our scores went up to about 60%. And at that point, we launched the Allen AI Science Challenge. So what we did was we made several thousand 8th grade science questions, again, four-way multiple choice, open to the community, and challenged the community to see if they could build systems that did well on this. And we had a lot of uptake on this challenge. We had, I think it was 3,000 downloads of the data set. And 750 entries in the competition. But even after all that work, the best systems scored just under 60%. And that led to this article appearing in the business magazine saying the best AI still flunks 8th grade science. And this really reflects the difficulty of answering science questions, as I illustrated at the beginning. Then in the years after that, we continued to add a couple more reasoning methods to the ensemble that we had. And then, of course, the most dramatic thing happened last year with the advent of language model technologies. And when we added in language model solvers into Aristo, we had this stunning boost in scores, taking the scores on our 8th grade benchmark to over 90%. And this has, quite frankly, kind of blown me away, seeing this big increase, particularly if you think, as you get higher scores, it gets harder and harder to get extra percentage points out. And I'm going to spend some time in this talk delving into why why that happened and what's going on inside. I should say we also tested Aristo on the 3 latest New York Regents exams. That was the examination board we were using. So these are exams from 2017 to 2019. These were not part of the original benchmark, and again, Aristo scored 93% on those. And we've also tested on 4th and 8th grade science, and we still 4th and 12th grade science. We still see the same general performance curve. So this isn't just a kind of statistical fluke. This is a real phenomena that we're seeing. So let me just pause for a second and ask if there's any questions. Okay, in that case, I'll move on. So I'm going to do 4 things now. I'm going to ask first of all, how does Aristo work? And just give a very brief look inside at some of the machinery that's there. I'm going to then delve into a bit about what's going on behind the high scores on the exams, particularly looking at the language model components. And in particular, one thing which has really interested me is, are these systems just doing fancy pattern matching, or is there more going on inside? Is there some hints that the system's reasoning? And I'll talk as well about where Aristo fails. So if it's getting 90%, that means it's getting 10% wrong. And there's some quite interesting patterns in where it makes mistakes. And then finally speculate on what's the way forward and some of the work that we're currently doing. So firstly, how does Aristo work? So Aristo is an ensemble architecture. So this is a kind of overly simplified architecture. So Aristo has 8 different solvers, which each independently try and answer the question. And then there's a combiner, which is trained to combine the confidences of the individual solvers together, so come up with an overall answer. And the different solvers can be organized into loosely 3 different families. So there's the retrieval and statistics solvers, there's the inference solvers, and then there's the ones using language models. So the retrieval and statistics solvers, I'm not really going to say much about those. Just as a very quick overview, the retrieval system basically takes a question and an answer option and looks in a giant corpus to see if the answer's been written down somewhere. So it's kind of a lookup solver. And then we have a couple of statistical-based solvers, which look at the word correlations between question and answer options and use point-wise mutual information and other statistical methods to look for answers that seem to be highly correlated statistically with the question. And there's more details about these solvers in our archive paper and other publications about it. Secondly, we have a family of solvers which attempts to do more structured inference with knowledge that we've accumulated about science. And I've just mentioned two of those. So the first one uses a large knowledge base of information stored in a large collection of tables. And so let me just illustrate that with this question here. So the question reads, in New York State, the longest period of daylight occurs during which month? And here the correct answer is June. And so how would you go about answering this question? You know, what knowledge is needed? Well, if you think about it, well, we need to know, you know, how does the day length change in different months and different locations? This question is appealing to knowledge about the different solstices and when they occur. We also need to know where New York State is, it's in the USA, and in particular, which hemisphere is it in, and so on. So these are the different bits of knowledge we'd need to answer this question. And we could just try and put this knowledge in ad hoc or try and retrieve it ad hoc, but we can represent this a bit more systematically as a collection of organized tables. So here's an example of some of the tables in Aristo's table knowledge base. So we have information about countries and subdivisions and so on. So to then actually answer the question, we also have a reasoning algorithm which attempts to find a path from the question to an answer by traversing elements in the table. So I'll just illustrate this graphically. So we can find from the question, we can see additional inferences, New York State's in the USA, longest period of daylight is the summer solstice, USA is in the Northern Hemisphere, and the summer solstice in the Northern Hemisphere is in June, and so on. And now we get to one of the answer options. And as you can imagine, there's many different paths that you can take through these different tables. And so we have used a integer linear programming method to cast this search problem as a constraint satisfaction problem. So the goal is to find the kind of graph of connections which best matches a set of hard constraints and soft constraints. So for instance, there has to be a path between the question words and the answer, then it needs to be connected and so on. And we use integer linear programming to solve that constraint satisfaction to find the best supporting graph and come up with the answer. So that's kind of a very top level picture. Again, there's more details in some of the papers about it. And I'll mention one other structured reasoning solver we're using, which is called tuple inference. And so the intuition here is that we can distill from our text corpus basic units of knowledge in the form of tuples. So subject relation object triples, or maybe subject relation object plus additional arguments. And then instead of trying to answer a question by just retrieving sentences, we can see if we can create a patchwork of triples that may support different aspects of a question. So to illustrate in this case, so this particular question reads, which object in our solar system reflects light and is a satellite that orbits around one planet? And the answer here is Moon. The tuple retrieval system will retract a collection of tuples that seem to be relevant to the question. So here's some examples here. And again, we look for a support graph which connects as many of these retrieved tuples as possible to the question. And again, we can formulate this as the inference problem as a constraint satisfaction task. Again, both hard and soft constraints. For example, we want to cover as much of the question words as possible. We want tuples to connect questions to a particular answer option and so on. And so for the answer option that has the stronger support graph, we'll pick that particular option. So again, that's just a sort of quick graphical picture of how that system works. And I'll mention its performance in just a second. The third family of solvers, which have kind of changed Aristo dramatically, and these now carry most of the weight of the problem-solving behavior. The new language models, particularly BERT and Roberta. So we've made extensive use of those. And so the way those systems work, this is just showing BERT. We take a question and a particular answer option, and we'll feed it into BERT, along with 20 sentences that are retrieved from our large text corpus. So Aristo uses a web crawl of about 1/3 of a terabyte of text, and so we'll get a bunch of relevant sentences. And then BERT kind of, you can think of it as sort of reading this text to loosely say it sort of ingests it at least using this form on the right. And then we come up with a confidence in this particular answer option by projecting the CLS token to a single logit. And then we do this for the 4 different options, do a softmax over the 4 logits to get a overall probability of each answer option. And then of course we select the answer with the highest probability. We train this using cross entropy loss, and that gives us our solver. And so just to show the impact of BERT and Roberta on the scores, this was the score of Aristo on the benchmark at the beginning of 2019, about 73%. We added in a new solver earlier in last year, which was based on textual entailment, and that raised the scores up to about 79%. Now, if we take BERT and just train it on our science questions without doing any information retrieval or anything else, it does well. It gets about 67%. So it's not a dramatically high number, but it's still good. We then did 3 things to further improve it. So the first of those was to add this information retrieval step, as I described just a few slides ago, where we give it not just the question, but a set of relevant background knowledge retrieved from the corpus. The second thing we did was we trained it, or fine-tuned it, I should say, using a curriculum of increasingly specialized training data. So we first of all trained it on general multiple choice questions using the race data set, courtesy of you guys at CMU, so thanks for that. We're not quite sure why it's so effective. We think it probably helps Aristo just to learn how to do multiple choice questions in general. And then we further fine tune it using general science questions, and then further on the Regents exam that we're looking at, and that leads to the overall system. And then thirdly, we ensemble 3 different versions of BERT together. And when we do all that together, that sort of modified BERT we call Aristo BERT, that on its own scores about 83%. When we combine it into the ensembler, the numbers go up to about 87%. And then with Roberta, we can do a similar thing. Roberta does even better. It gets up to 88% on its own. And then when we combine it in, it gets up to 91% combined. So this is the kind of sum total of all its components. And so again, this is a pretty startling success. And as I say, it's really, in my mind, reflects the huge progress that the field of NLP has made as a whole, and particularly with the advent of large-scale language models. It's a huge tribute to what the field has done. And I mentioned we see similar progress bars on 4th grade science. So this is the 4th grade progress. And so even more surprisingly for us, we see even the 12th grade questions, which are really difficult, go up to about 83% on again on the non-diagram multiple choice questions. So again, really exciting. If we look at the performance of the individual solvers, they look like this. So what I'm showing here is 4 different collections of questions. So 4th grade, 8th grade, 12th grades, and various combinations of our larger data sets. And the green bars here represents Aristo as a whole. And let me just zoom in on the Regents 8th grade questions. And what I want to highlight here is these last 2 bars here represent Aristo BERT and Aristo Roberta, the 2 language modeling solvers. And as you can see, it's really these 2 solvers which are doing most of the heavy lifting. You see that also in the other data sets we've looked at. And so that raises this really interesting question about what's going on. And so what we want to do, and what we have been doing, is some detective work to try and dig into the language model solvers and see what they're doing. So that's kind of where I want to go to next.
Oh, Peter, we have a couple of questions.
Great. So I was just going to pause and ask. So yeah, go ahead.
Well, so on the chat, should I read them out? They're on the chat system here.
Okay. I'm not quite sure. Let me just see how to get to the chat.
So
I see.
Sricharan asks, can you speak a bit about the size of the data sets?
Oh yes, and I just see the chat here. Yes, so the fourth and the eighth, so the Regents data sets are fairly small. If I remember, I can't remember the exact figures. They're of the order of several hundred questions each for the fourth, eighth, and 12th grade questions. The ARC data set is our compendium of a whole collection of data sets drawn from multiple different examination boards, and they contain, I believe, there's about 5,000 in ARC Easy and about 3,000 in the ARC Challenge data sets. And I can see another question here. If Aristo is trained on data composed of the 8th grade tests, how does it perform on the 4th grade tests? So we haven't done exactly that transfer. The ARC Easy and the ARC Challenge sets contain a compendium of 4th, 8th, and 12th grade sets, which are a mixture. So we haven't exactly, that's a really interesting question. That's a great question about knowledge transfer. My expectation is if we trained on 8th grade, it would do very well on the 4th grade tests. And the reason I suspect that is because the division into 4th and 8th grade questions is kind of a sliding scale. So we find 8th grade questions that are really quite easy and would fit in the 4th grade level, and similarly 4th grade questions that are pretty easy, pretty difficult, and would fit in the 8th grade format. So I'd imagine there's fairly good transfer between it, but we haven't actually transferred that. And then there's a question, is there a way to test if there's some true understanding versus whether the model captures some surface level pattern? That's a great question as well, and I'm going to talk about that in the next section. And then finally, there's a question, how do you retrieve relevant text from the large corpus? We're using Elasticsearch, so there's nothing particularly clever there. We're now doing experiments on training the system to do better search. So using vector encodings of the text and vector similarity to do better retrieval. We found in most recent experiments, we can do a little bit better than Elasticsearch, but not a huge amount better. So just using Elasticsearch is doing reasonably well at the moment. And I just got to, right. And if there's no other questions, I'll continue now. All right, so what's going on behind the high scores on the exams? So we've done several probes to try and work out, what's going on inside. So the first probe we did is quite a common test, which was looking for annotation artifacts. So it's quite well known now that systems can often sneak their way to a correct answer. And one of the most common tests is, can the system guess the right answer, just given the answer choices without even looking at the question. So we did this test where we trained a language model, just giving the question answers. And what we found is the system just trained on the answer only data set scores 37%. So it's a little bit better than random, which would be 25%, but it's not a huge amount higher than random. So we see in the 12th grade, it's a little bit higher than that. It gets up to 47%. So this low score is actually somewhat reassuring for us. It shows that at least for the officially written science exams, it's quite hard to do well just by looking at the answer choices. And this is quite a stark contrast to the crowdsourced data sets, which are quite common in AI these days, where often crowd workers will sometimes be lazy and use giveaways for false answers that neural systems pick up on. So that was one test we did. The second question, which is kind of interesting, is can we fool Aristo by giving it obviously wrong answers? So we're using 4-way multiple choice questions. Suppose we made these 400-way multiple choice questions, and in particular look for whether any of those options would fool it. And so we created a kind of adversarially generated data sets where we can deliberately look at giving Aristo, say, 400 options and see if any of those do fool it. We do find indeed there are options which fool it. And so we created a kind of adversarially generated 8-way multiple choice questions, deliberately picking questions which we see falls the original language modeling system. So a modified question looks like this one. So the question says, the condition of the air outdoors at a certain time of day it originally was asking is known as friction, light, force, or weather being the correct answer. And now we've added in the crazy answer options, joule, gradient, trench, or out heat. And so no students who even had a basic understanding of science would ever pick these options. But we find often Aristo does select these incorrect options. This is arguably an unfair test because, as I said, by definition, we've picked options which we know fool the system. So a fairer test is to say, well, given this adversarially generated data set, suppose we now fine tune on this data set, how well does it do? And we found when we retrain, in fact, Aristo does largely recover its performance on getting the correct answer options. So specifically, we find it goes from 69 or on Pendy down to about 50%. So we do see a drop of about 10 points. And remember, we're going from 4 random guess. So I think the conclusion for this is, Aristo is not completely robust to crazy options. There is some evidence that it can be fooled. It can learn to avoid crazy options, but it means it's not totally robust to this kind of attack. And then the most interesting question, and this is to the question that was asked on the chat, is Aristo doing more than pattern matching? And we do observe some interesting behavior. And so what I want to do, if I can, now let's see if I can do this. I'm going to switch to a different screen here and just see if I can do a quick, find the right page. Just bear with me 1 second. Okay. So that looks like the wrong one. Let me just try another one more. Here we go. That's the one I wanted. So what I'm going to show here is what you're seeing here is a question. Here, this is Aristo, the life system. And so here's a question which is actually quite challenging for Aristo. It says, city administrators can encourage energy conservation by lowering parking fees, building larger parking lots, decreasing the cost of gasoline, or lowering the cost of bus and subway fares. So this is quite challenging. The correct answer here, if you're looking at it carefully, is lowering the cost of bus and subway fares, because if bus fares are lower, presumably there'll be more public ridership and less people driving, so that's good for energy conservation. So if we give this to Aristo, it's going to chug away, and here it's got the right answer, which is pleasing. But what I want to show is if I now modify this question, I'm going to change lowering to raising, and I'm going to change decreasing the cost of gasoline to increasing the cost of gasoline. Now I've changed this question, and so now the correct option should be option 3. And if I give it to Aristo, sure enough, it does actually change its answer choice to option 3. So more gasoline is going to discourage driving, encouraging energy conservation. And again, if I mutate this system instead of encourage, I'm going to say discourage, and I give this to Aristo again. And again, it's changed its answer option again back to raising the cost of bus and subway fares. So this is interesting. Aristo seems to be correctly responding to these kind of subtle changes in wording, and it's suggesting it has some knowledge of some of the semantics about qualitative change and negation. So the question here now is, you know, is this just a fluke, or can we be more systematic and test this? So I'm going to go back to my original PowerPoint here, and I'm going to what I'm going to do here is now let's think in terms of a scorecard for Aristo, and we're going to test Aristo about whether it knows about negation, conjunction, polarity, and so on. So how can we test whether Aristo really understands or has some understanding of negation? Well, we can give it a set of synthetic tests, and so the tests we give it kind of look like this. So we give it fictitious inputs like this as context. So instead of the information retrieval, we'll give it these statements like Alan is small, Alan is tall, Bob is big, Bob is tall, and so on. And then we're going to ask a question like, which of the following is not tall? Alan, Bob, Charlie, or in this case, David, which is the correct answer. And we're going to give this to Aristo without any fine tuning on this data set. So this is completely zero shot. Aristo has no training on this kind of data. And remarkably, we find Aristo gets these questions right with 94% accuracy. So this is, again, quite surprising. And it suggests that when we observe Aristo reacting correctly to negation on the real science questions, it's not just being lucky, it has some systematic knowledge about negation in the context of question answering. So we'll give it a grade A here using the standard rubric. So we'll give it nice work here. For conjunction, again, we can test this in a similar way. So again, we'll give it context like this. Again, randomly generated statements. Alan is big, Alan is red, Bob is blue, and so on. And ask questions like, which of the following is big and blue? Is it Alan, Bob, Charlie, which is the correct answer here, or David? And we find with just one conjunct, again, Aristo, again, this is out of the box without any fine tuning on this data set, gets 98%. With 2 conjuncts, 95, and up to 4 conjuncts, it gets 80%. And if we throw in a negation as well, the scores go down a little bit, but still stay as high as 75%. Again, this kind of blew me away when I saw it. To give you just an example of 4 conjuncts and negation, here's an example question. We have a big context, and then the question is, which of the following is old and red and light and big and not short? And the correct answer here is, well, I'll leave this as a kind of exercise to the reader to work this out. So you can see it's not an easy question to answer, and Aristo's answering these correctly 75% of the time. So again, this is pretty startling. And so we get, so as the scores I showed you, they're between 80 and 98%. We'll give it a B+ using the standard rubric. And I'm just going to open the chat window just in case there's more questions. If you have questions, please feel free to type them into the chat window as I can see them. Thirdly, let's look at polarity. So this is the kind of behavior which I mentioned earlier, where we can flip something from greater than or less than. So we'll start off with questions that are actually quite difficult in the first place. So here's an example question. We'll give a context. Sound has a slower speed at lower temperatures. And then we'll give it a question like, if Jim turns his thermostat down in his room while listening to music, what will happen to the speed of sound waves in the room? So the correct answer is they will slow down. So we'll want Aristo to both get this question correct, and then also we want to be able to flip the polarity of this question. So instead of saying down, we'll flip it to up. And now this should change the answer option from slowing down to speed up. So to get a point, Aristo both needs to get the original question correctly, and here we're using 2A multiple choice, and the inverted question correctly with the flipped answer. So as part of a separate bit of work, we generated a large data set to test this, and we find, again, out of the box, Aristo gets about 67% here. Again, the baseline for this is about 25%. So again, using the standard rubric, we'll give it a score of D+. And I mentioned here, you could ace this with more study. We know if you fine tune on this data set, the the system can get scores up in the high 90s. So again, this is without fine tuning on this data set. We get scores of about 67%. And so there's a couple of questions which just appeared. So one question was, do we find a pattern of errors that Aristo made in the negation task? That's a really good question. We've looked at some of the failures. We didn't see any obvious patterns in the negation task. So it's a little bit of a mystery to us why it doesn't get, so it's getting 94%. Why are there, why is it getting the 6% wrong? So we didn't find any particular patterns. Again, that's a great question to ask. And then another question, is the system retrained for each of these subset of queries, or is it transferred from the science exam data? Again, great question. Absolutely no retraining done. It's completely transferred from the science exam data, which is again why it's so surprising. As I mentioned, we have also tried retraining. It aces all these data sets quite easily with retraining. The more surprising thing is the retraining that the transfer from the science domain data. So I won't go through the other tests except to say it similarly does well on several other tests we did, with one exception, which is counting. So an example, so we used I think it's task 14 from the Babi data set of counting, which have slightly weird questions like this one that I show here. Daniel picked up the football, Daniel dropped the football, Daniel got the milk. How many objects is Daniel holding? The answer is 1. Aristo does terribly at this. It has no idea about how to count, at least in this way, and so we give it an F here. So my takeaway from all of this is that, is Aristo just doing fancy pattern matching with sentences? No, there seems to be a lot more going on. It has some kind of knowledge, some sort of systematic knowledge about some of the semantic phenomena that it needs to handle. And this is undoubtedly why it's getting scores, at least in my mind, from the high 70s up to the up into the 90s. But then, as you can see, at least without any fine-tuning on these data sets, that knowledge is not 100%, so it is making errors. So it puts language models in this kind of strange situation that it seems to have some sort of systematic knowledge, but it's not kind of the kind of perfect understanding that a person would have. And that makes them extremely interesting as objects to study. So again, I'll pause if there's any questions beyond those on the chat. And if not, let me continue. So I mentioned Aristo gets 90%. It's really interesting to look at where Aristo fails. So it's getting some questions wrong. Is there some systematic pattern to the ones it's getting wrong? So what we did was we took 30 questions which Aristo got wrong and did a sort of detailed analysis of those. And in particular, looking at the language model's performance. And because we have this information retrieval step, we can do something quite interesting. So recall that the language model works by we give a question answer option, we give it some retrieved text, it reads this and gives an answer confidence. This allows us to look at the retrieved knowledge it was using, and in particular to say, well, for the questions it's getting wrong, did it just not find any relevant knowledge, and so it kind of couldn't even get started, or did it find good knowledge and it just couldn't make sense of it or got confused? So when we look at the questions that it got wrong, we see this interesting distribution. So out of 30 failures, only 4 of those did we find it retrieved good support for the correct answer. In other words, based on the IR results, it really should have got the question right. So the fact this number is so low suggests that if Aristo does get relevant knowledge for answering a question, it invariably does get a good answer. And I'll mention a couple of questions where it got fooled, but as I say, they're fairly unusual. There was one case we saw where actually it retrieved good support for an incorrect answer, and I mentioned those. The majority of failure cases, it didn't retrieve any good support. And there's some interesting classes of question here which are worthy of further study, and that's where we're going now, and I'll show those. And then there are 8 questions which are of a different style to many of the other science questions, which are more reading comprehension questions. And again, I'll illustrate those. They're questions where IR really is not going to be able to help. And let me just address one question which just appeared in the chat question. The question says, counting problems would seem to require some internal states and transitions in an internal world model of a situation. So it'd be strange if that worked without a mechanism to build it in. So I think that's exactly right. Counting does seem to require, I think, some notion of internal states and transitions. Having said that, I have seen other results where, so we have another data set from AI2 called the drops data set, which seems to imply require some sort of numerical reasoning, and transformers do seem to be able to do some sort of counting. There's been one system, I think the paper was give Bert a calculator, which does exactly what's suggested here, essentially giving a little calculator with internal states. And yeah, so I agree. It would be strange if counting did work without some internal states. There's one other thing I'll just mention as well. It's not just counting that requires world states. There are a bunch of problems which require reasoning about processes and changing states in processes, which also seem to require modeling world states. Again, Aristo struggles with some of those problems, and I'll mention some of that as future work that we're looking at now. So let me just delve into this pie chart here just for a little bit, because it's kind of interesting. So let me first give an example where Aristo got fooled where it shouldn't have done. And so the example question is this one. Which is the best unit to measure distances between Earth and other solar systems in the universe? And so the correct answer here is light years. Aristo got the wrong answer, which is astronomical units. So I don't know if you physicists out there, what is an astronomical unit? It's actually the distance, if I remember right, it's the distance between the Earth and the Sun. And so it's used to measure distances within the solar system. Aristo should have got this question right, because part of included this sentence here: distances between Earth and the stars are often measured in terms of light years. But he got fooled by this IR for the incorrect option, which says, in general, distances in the solar system are measured in astronomical units. So what's happened here is essentially Aristo's got confused about the difference between within a solar system and between solar systems. And it's taken the question to be talking about between solar systems. It's kind of a subtle difference. When I've shown this question to other people, humans have got confused with this as well. So arguably we should be give Aristo some lenience for getting confused with this. And as I say, this is more the exception than the rule. Generally, if there's good IR, Aristo gets the question right. Here's a question which he got. There was support for the incorrect answer. So the question reads, which of these objects will most likely float in water? And it guessed a rubber ball, even though the correct answer is tennis ball. And in fact, if you look at the IR, there's a bunch of sentences which say, indeed, rubber balls do float. Arguably, this question requires a bit more subtlety here. So we really should have Aristo know about the phrase most likely and do comparisons across different answer options. Because of the way we've set up Bert and Roberta, it's not able to do cross answer option comparisons like that. And so it's not able to do that kind of comparison. In this case, it just assesses each question option, each answer option independently for how likely true it is. And so it gets confused here. Thirdly, there's the question of if there's no support for the correct answer. So we find the majority of cases there's no good support for the correct answer. And so this isn't just a failure of the information retrieval. Sometimes the questions require combining several bits of information which really look fairly different to the original question. So an example is this question, which I'm showing you here. The question asks, what's the difference between an eagle and a pelican? The correct answer is they're a method of catching food. And Aristo guesses their method of reproduction. So it struggles here because there are no sentences in the corpus which compare eagles and which talk about eagles and pelicans together. What's really needed to answer this question is retrieving information about eagles, information about pelicans, and then doing some sort of comparison. Aristo has no notion of problem-solving methods like that, and so it struggles with that. And then another question that fails is, interestingly, the question I showed you at the beginning about how the particles in iron affected when it's melted. Again, the corpus has statements about high temperatures cause particles to vibrate quickly, and melting causes high temperatures. But again, those bits of information look rather different to the question, so the IR doesn't find them. And even if the IR did find them, Aristo probably doesn't know how to do that kind of sort of comparison, combination of different sentences like that. And some of the recent work we're doing is actually trying to train Aristo to do that kind of comparison. I'll just briefly mention story comprehension questions. Aristo is not really trained for that. So in this example here, there's a description of an experiment, and then the question is, what's the independent variable? So clearly, doing information retrieval here is not likely to help, and so Aristo guesses the incorrect answer. And similarly, questions about sentiments. So here the question asks, which statement is an opinion? The answer here is many plants are beautiful. Aristo again looks in information retrieval and thinks its plants require sunlight. Again, these kind of meta questions are outside its basic problem solving ability. And then one final question, which I thought was really interesting, which we thought it should have got right, about how long does it take for the moon to complete one revolution around the Earth? Correct answer is 30 days. And the information retrieval has a lot of good supporting evidence that it takes about 27.3 days to orbit the Earth, 27.3, 29.5, and so on. But Aristo has no idea that 27.3 is close to 30. And so instead it guesses 365 based on information retrieval results for that answer, which presumably talk about the Earth revolving around the sun. And so it gets confused there. So again, very interesting. There's a whole collection of categories of questions which, besides the ones where Aristo got fooled by the syntax, large categories of questions which Aristo really can't get started on without more sophisticated problem-solving capabilities. So what I want to do now finally is talk about steps forward and how we might address some of these categories. So I'm going to mention 4 different categories. The first is question decomposition, which I've sort of hinted at before, again showing another example question. What virus structure is similar to function to a cell membrane? The IR produces a lot of junk, so there's nothing here about the function of a cell membrane and so on. Really, we need more of a problem-solving method approach here, where we break down the question into its components. So for instance, we'd like the system to ask, well, what's first the function of a cell membrane? Okay, it surrounds and protects things. And then what part of a virus surrounds and protects it? Okay, it's the protein shell, and now we have the answer. So we've done some recent work in trying to take complex questions and break them down into more modular pieces where we can use the now pretty high quality question answering capabilities of neural systems. So this is one big area of research. The second is doing more systematic multi-hop reasoning, again, where we have to do multi-step retrieval. So another good example here is this question: which conducts electricity, a suit of armor or cotton candy? So again, our corpus has nothing about armor conducting electricity. You'd have to do some sort of multi-step retrieval, and different groups are looking at this now. So for instance, first of all, we might retrieve things about electricity conductivity, and then pivot from that to ask about other information in the corpus that connects those first retrieved sentences to the answer. For instance, including that suit of armor is made of metal and other things like that. And now, can we combine facts from the first and second retrievals to form something of a chain of reasoning? For instance, suits of armor are made of metal, and metals conduct electrical current, to conclude, therefore, it's justified that suits of armor conduct electricity. So this would be a good kind of informal chain of reasoning. But of course, we can't just arbitrarily combine sentences. So for instance, a sentence about resisting arrest really doesn't form any sort of useful pattern to connect to the conclusion we're interested in. So again, this requires not just better IR, but some form of kind of neural reasoning across sentences. And I'll mention in a second some exciting work we're doing to try and do that. The third area, again, thinking about, does Aristo really understand science and the world, is does Aristo model world states and have some modeling of world states? In fact, before I go into that, let me just mention a question which somebody just asked. Have you tried this multi-hot reasoning over knowledge graphs? I'm guessing that just over text, it would be more unstructured. We haven't explicitly tried it over knowledge graphs. There have been other groups that have tried this over knowledge graphs. There's been a lot of work on the Hotpot QA data set trying to do reasoning over knowledge graphs. I think that would be an interesting way of doing this. To do knowledge graphs, we'd have to convert our retrieved knowledge into some sort of tuple structure. Again, I think that would be a great avenue for further work. Knowledge graphs gain something with a structure, but then of course you lose something by converting into the knowledge graphs. Good question. I think it would be very, very interesting. As I say, I'll put you to the Hotpot QA work where people have done quite a lot of work on knowledge graphs. Let me just talk about this modeling world states. So this is kind of interesting. A lot of science involves processes. If I give you this paragraph of processes, it's describing a sequence of steps. If we read it, suppose we'd read the first sentence, roots absorb water from the soil. You and I will create a mental picture in our head. Okay, there's a plant, it's got some roots, the roots are in the soil, the roots are absorbing water, and then the water flows to the leaf. And so we'll imagine the water flowing to the leaf. So we create this picture in our head of what's going on. And if we do that, we can then answer kind of complicated questions about the process. If I ask, for instance, where is the sugar created? You and I would say, well, it's obviously created in the leaf, as that's where all the ingredients are converging on, even though it's not stated anywhere explicitly that that's what's going on. Because the computer has no model about state and change of state, it has no idea about such questions. If we give this question to BiDAF, for instance, we get this crazy answer, light, water, and CO2. And so we're doing a whole lot of work here about trying to model states and world states and how they change to try to give the neural system some kind of memory about the world and how the world's changing. And that's including really interesting work with one of your students here and Ed Hovey's group. So again, this is work I'm really excited about. And finally, of course, and this is probably the most exciting way forward, we don't just want a system to get the right answer. We'd like it to be able to explain why it gets the answer, and in the best case, be able to correct the system's misunderstanding. So to illustrate that in a kind of fictitious dialogue, if I asked, can you pick up a penny with a magnet? Suppose Aristo says yes. We'd like to ask why, and the system might give us some answer based on its knowledge it's using, for instance, because pennies are made of metal, and metals are magnetic. And then suppose there's a misunderstanding here. We'd like to be able to correct the system's knowledge. We might like to say, well, actually, not all metals are magnetic. Copper is not magnetic. And then say, try again. And the system now updates its knowledge and retrieves different sentences and say, okay, I see pennies are made of copper and copper is not magnetic. So therefore, you wouldn't be able to pick up a penny with a magnet. So this is a kind of idealized state we would like Aristo to get to. And in order to do this, we need to train Aristo not just to get an answer right, but also to be able to reason, do some kind of deductive or plausible reasoning across sentences. So how might we do that? Well, you could imagine trying to train a neural system to do this. So we might give a training example like this. Metals are magnetic, nails are made of metal. Are nails magnetic? And we want it to produce the answer true. And that's just to make sure it's not just answering the question based on its pre-training. We can force it to kind of read the context we're giving it by giving it a kind of counterfactual situation. Metals are not magnetic. Nails are made of metal. Are nails magnetic? Now we want to give the system to give the answer false. So it's very unclear whether a neural system can learn this kind of reasoning. So this is rather different from just finding an answer span, and it's very different from just using pre-trained knowledge. Can we train a system to do some kind of systematic reasoning across sentences the way us old folk used to do with formal reasoning systems in the past, but now doing this with language? So how might we train a system to do this? Well, we can generate a bunch of theories, and what we did was we used a theory generator, generated some logic theories. We can then convert them into natural language or pseudo-natural language using text templates. And so here we've got questions about, again, fictitious people. And Bob is big, and big people are rough, and rough people are green. So is Bob green, true or false? So how can we generate an answer to this? Well, we can answer this question using a theorem prover, using our original formal theory. And so the answer is true. And so now we have a training example. So this is great. And we can generate thousands of examples like this. And sure enough, to our surprise, neural systems are in fact able to learn this kind of reasoning over language. And that produces a very interesting reasoning system. So kind of hot off the press, we have a system called Rover. And again, I'm just going to pause my screen here and just see if I can give you a quick demo of that. And again, sorry, I failed. Let me just have a look here. Here we go. Okay, so this is our Rover system, and I'm just going to feed in some facts here. So I'm going to tell it metals conduct electricity, and iron is a metal. Insulators do not conduct electricity. And I'll say nails are made of iron. And now I'm going to ask nails conduct electricity. And if I submit this to the system, it's going to reason and tells me true. As expected, how do we know it hasn't just memorized the fact? Well, suppose I change this and say nails are made of plastic. And I'll say plastic is an insulator. And now I'm going to ask the question again. And now it's produced the prediction. You'll see at the bottom, nails conduct electricity is false. So it's apparently chained these sentences together. And again, I can play around with this. Plastic is I'll say counterfactually, plastic is a kind of metal. And now I'm going to ask this question again. Do nails conduct electricity? Now the answer is true. So this is pretty surprising. We seem to have being able, at least in a restricted setting, to train it to do this kind of reasoning with sentences. And this provides at least an initial venue to do the kind of reasoning that I mentioned, where the system can not just give an answer, but can show the sentences it used and provide some kind of justification for that. And this demo is available. This demo is available online. You can go to alanai.org and Aristo, and you'll see some pointers to that. So let me just check the chat message again as well. And so let me just finish. So let me just finish this presentation. So just in summary, we've had surprising success with language models. And the thing which is interesting, it suggests that structure is not essential for many tasks. It's kind of embarrassing for old style AI people like me that we can get away without necessarily structured knowledge bases. And I've tried to show that the language models are doing quite a lot more than just pattern matching, but doing some interesting reasoning. But also, as I've shown you with the failure cases, there are numerous types of questions which Aristo is falling short on. There's a lot of work to do to take AI and question answering to the next level. So what do we need going forward? I mentioned a bunch of ways forward. And I think most importantly, there's a need to reintroduce some kind of structured reasoning, but it's less the kind of formal structured reasoning that AI studied in the past, but trying to do some kind of structured reasoning, using language-like representations. And so, again, thank you for your attention. I hope it's been all right. I know it's more challenging maintaining attention with remote presentations. Thanks for the comments over chat. And so I'll stop at this point and take any verbal questions or chat questions as you like.
My attempt at playing applause sounds didn't sound like it worked.
Okay, no worries.
Thank you, Pete. Thank you very, very much. I don't know if anyone else has questions, I'm sure, but I have a question that I've been struggling to formulate that maybe I'll just kick off with this one and then you can take it, other people can maybe riff off or think in the meantime. So what I like about this talk and about the work, of course, is how amazing it is and how it sort of says things that we wouldn't have thought possible even 5 years ago. What worries me about the talk is you didn't say much about how you think it actually does work. I mean, it's not magic inside there, right? Something is going on. It's doing something. So I'd like to propose a simple picture and then you can shoot me down. Okay?
Yep.
So all the examples you showed of the more complex things, you have these sort of little chained triples, you could sort of say. Something is magnetic and something is, magnets do something, something is made of metal, metals are magnetic, whatever, middles, and then you can sort of hop the properties
Ed, you're breaking up kind
of through the pivot point video. Sorry, this is a complex question, but I want to say it in a way that I'm just trying to explain what I'm thinking. Why can one not say that since BERT and Roberta and the other embedding engines, these models are just essentially n-grams, as you say, right? It's just language models. And instead of having words with their contexts, like a transformer learns, they have word parts with their contexts. So they're learning things like and then the root, negations and pieces, even if it's part of the morphology. So if you imagine that you have inside these models a sort of an n-gram, not a triple, but a more complicated multi-part, multi-unit pattern, and you've got a bunch of them sitting together. And now you give these different sentences, each one of which breaks into its own multi-part little structure with pieces there, each piece being a root of a word, but generalized to have sort of similar synonyms and things like this. And you allow them to tile across one another and to pivot, just like your simple triple-based examples where things are metals and so on, pivot on one another. Why can you not say, why could one not say that what it's doing is just learning how to tile these little pieces together and match until it comes up with something that looks like the right answer, the thing that best pivots all the pieces together?
That's a great question, and it's one thing that we've been looking into and sort of struggling with to understand. So let me give two comments. So the first comment is we've thought a lot about what's going on inside this transformers when it's doing this kind of reasoning. So one hypothesis, if we look inside the layers of BERT, maybe in the intermediate layers we see intermediate conclusions. So potentially we could probe that and see, you know, are there really some kind of chain of reasoning going on? If that was the case, maybe it's limited to depth 12 chaining because it's a 12-layer transformer. The second option is that maybe it's just simply memorizing somehow kind of all the proof structures it's seen in training, and that actually, although it's giving the I/O behavior of doing reasoning, perhaps it's actually just got a large knowledge base of proof forms that it's working with. And then a third option is maybe it's just doing something completely different that we can't quite understand. So I don't know the answer to that. And then the second comment is with regard to kind of, is it just tiling n-grams together to come up with an answer? That may be the case. I mean, you could imagine, well, I think it must be doing something more than that, because if it was just doing tiling n-grams together, would be kind of like finding chains of sentences, chaining on word overlap together. And we find with the rules we're putting in, just having sort of word overlap patterns doesn't fool it. So inference, it is partly doing some sort of chaining, kind of think of combining tiles together, but it's avoiding tiles which are not justified conclusions. So I think there's more going on to that. You could imagine simplifying the kind of pseudo natural language rules we put in, and putting in trigrams or something like that, and exploring that hypothesis more explicitly. But it seems to be doing more than that.
So I would guess, just as a concluding remark, I would guess that if one doesn't think of this a linear tiling of n-grams, but sort of structures, a 2D tiling of pieces, I would guess it would be interesting to investigate that, and not just n-grams of words, but families of words that are sort of equivalence class together, much more sophisticated kind of n-grams, because it's doing it's not doing magic. And these things are very simple in there, right? It's just basically an n-gram store, or a generalized n-gram store. That's what they are. So
that's true, but some of the answers we're getting are quite complex. So, for instance, those 3 conjuncts or 4 conjuncts of negation, you're asking, is A and B and C and not D true? Maybe it's doing some complex tiling of n-grams, but if it is, it's quite a complex tiling.
Yeah, yeah.
I think it's a great question, and I think this is going to be a big area for investigation going forward. Not just AI2. I think the whole field is looking at, as we find transformers are doing more and more, what exactly is happening inside, and what are the limits? And clearly there must be limits. I mean, it's exactly right. They're not magic. They're doing some sort of clever, sophisticated pattern manipulation. What can we use it for, and where does it break down?
Yeah.
I think Scott had a question. I saw him raise his hand in his video, and then there's also another question in the chat.
Go ahead, Scott.
Yeah, hi. Very interesting talk. If I understand what's going on in here, the only knowledge in the system is searchable but undigested text, huge amounts, and then whatever's hidden inside BERT.
That's pretty much true, with the addition of, we also pre-trained Aristo on several thousand science questions, and then on the race data set, which is about I think 100,000 comprehension questions.
Okay, and where and how is that stuff represented?
That's represented as additional fine-tuning on the weights within BERT.
Okay, so a couple of thoughts. First of all, your last point here with language-like representations. And of course, the Achilles heel of language-like representations is that language is ambiguous. And that can cause all sorts of trouble, although it may not ruin your score too badly in multiple choice questions. But you know, this kind of mouse is different than this kind of mouse.
For sure.
And one conducts electricity and the other may or may not. You have to catch it first. So that's one thing I would worry about. The other thing I would worry about is that something that I think our actual thinking leans very heavily on is inheritance through isohierarchies. This has been from the dawn of AI, people have known that that needs to be kind of central. And if you just treat that as n-step inference, you know, it can easily be 8 or 9 steps, just, you know, just to get that Clyde the elephant is an animal and therefore could move. There's a bunch of steps there, and I don't know if it would be cheating, but somehow putting in some special machinery to handle that in particular would be I think, worthwhile.
Yeah, those are great points. So we haven't really explored too much the retrieval aspects, but certainly if we retrieve, nails, for instance, in that demo I showed you, you can think about fingernails as well as nails that you use on wood.
Yeah.
So there's word sense issues there. If we retrieve, nails are made of whatever it is, cartilaginous tissue or something like that, we'll have got incorrect facts. So yeah, as soon as we throw this open to an arbitrary corpus of knowledge, word senses, you're right, could certainly cause problems. I absolutely agree that inheritance and then, inheritance with overrides where specific information overrides more general information is really important line of reasoning. We're currently trying to train a language model to do that, and the evidence is it will do that, including using some of its pre-trained knowledge about taxonomies. So in this example, I showed earlier, I had to, in our original training, we forced it to only work with what was provided. Can we train the system to use what's provided plus its background knowledge? So maybe it already knows that, people are animals. We shouldn't have to state that explicitly. But having said that, I've been very taken with this work I mentioned earlier about giving BERT a calculator, where one bolts into a neural system a reasoning module which has particular skills. So that particular work was done by giving it a numeric calculus. We've done experiments ourselves using a qualitative reasoner plugged in. Sure, maybe plugging in a reasoner which can do inheritance reasoning might be something it could learn to incorporate into its neural pattern matching at appropriate moments.
Well, if your big corpus includes a dictionary, there'll be an awful lot of ISA statements in there.
Right, that's true, and it could be a long reasoning chain. Though there might be statements that allow you to jump ISA as well. So as well, as long it's a big jump in word nets to go from man to organism, but there may be an explicit statement that's men or people or organisms.
Well, you could create those. You could sit back and
right.
And sure they're all there explicitly, but that tends to explode.
That's true. You could cache shortcuts if they're important. Absolutely.
Okay, thank you.
Okay, let's take Brendan's question from chat, and then probably we should end so that you have a few minutes before your 4 o'clock appointment.
Sounds great. Brendan, do you want to answer it verbally, just for variation?
Sure, I can do that. Yeah, I'm coming through, correct?
Yep.
Okay. So yeah, I was curious if there was any testing done with the ability of Aristo to kind of gauge its confidence. So the way I would imagine this is either having a none of the above response or possibly imposing like a penalty for guessing, where not only do you have to be able to do a sort of nearest neighbor matching for the question, you also have to know, okay, how close is that?
Yeah, that's a great option as well. We haven't explicitly trained Aristo on the none of the above, and I think that's, to be honest, that's one of the disadvantages about multiple choice question answering is, the fact it's one of the 4 answer options is a huge help in terms of answering the questions. The system does give a confidence on its answer. So the demo I showed you of Aristo earlier does assign a confidence that it gives, which is based on the logic scores. And so you can see when it's unsure between several answer options as opposed to very sure. And sure, we could train it to, we could add in some choices where none of the above would be an option. I think as well, the other thing generally, we're trying to move away from multiple choice now towards direct answers. I feel like the field has probably spent enough time and been perhaps too focused on just multiple choice. And there's too much of a risk of artifacts there to do that.
Great, I guess with that, I just wanted to say, like, I put the quiz link for everyone in the chat. It won't be sent over email, so make a note of it before you exit the talk.
Okay, and let's thank the speaker again. Since Bob, if you can't get the soundtrack to work, I'll just clap.
Thank you.
Okay, thank you.
Thanks also for your awesome questions. It was really great chatting with you. Great to have such an engaged audience, so I really appreciate it. Please stay safe. Thank you.
Okay.
Thank you, Pete. Thank you very, very much.
You're very welcome. Bye.